Welcome to our 12th lecture here in the Chemistry 51C series here at UC Irvine. I'm going to start off our lecture today by talking about the Glidden process and a famous steroid chemist named Percy Julian. Percy Julian started off as a professor at DePaul University and was hired by Glidden, which is still a well-known manufacturer of paints and paint products. And even back in the 1930s, they were well known as a company that made paints and varnishes and coatings. Here's an advertisement from 1937, right at the time that Dr. Julian started there. And Glidden was advertising, touting the fact that its paints were used to paint airplanes and all kinds of other things. Now, when you take oil-based paints that are used to paint airplanes or walls or ships, they have all kinds of additives in there. And if you want to have a profitable product, you want to make sure that you're adding inexpensive ingredients to your formulations. And one of the things that Glidden was adding to its paints, and maybe many companies, was vegetable oils, and specifically soybean oil. That's when you go to the store and you buy vegetable oil. It's soybean oil. And Dr. Julian recognized at the time that soybean oil contains small amounts of steroids, of steroid molecules, specifically steroid alcohols called sterols. And there was a big craze at the time to develop drugs based on steroids. Androgens like testosterone or estrogens or progesterone or corticosteroids for inflammation. These types of biologically active steroids are extremely potent. So just tiny, tiny amounts of these molecules exert profound biological effects. And one of the first commercially available steroid drugs was the birth control pill. Of course, you could inject progesterone and inhibit pregnancy, but nobody wants to be injected every day because that's a kind of a turnoff right there. But it was the advent of the orally available birth control pill that you could take in a pill form and prevent pregnancy that really made big money. Now, where do you get the starting materials to make steroids, kind of like progesterone or this drug that was developed, one of the first orally available birth control pills, ethinyl estradiol, or this ethinyl estrone molecule? Well, you have to start with a steroid in order to synthesize a biologically active steroid. It's not commercially viable. It's not, well, that's not true. It's not, at the time, it wasn't easy to get your hands on steroids using total synthesis. And prior to the development of the work of synthetic chemists in this field, you would have to go to a slaughterhouse and get hundreds of pounds of spinal cords or some other organ and then grind it up and extract out. You'd get tiny, tiny amounts of the steroids that you wanted. So you really needed a synthetic route. And the first viable route towards really blockbuster steroid drugs started off with a sterol, a steroid alcohol that came from these Mexican Barbasco yams. Man, look at the root or tuber on this thing. It's huge. It's the size of a basketball. And these particular yams, 5% of the weight of this molecule was this steroid alcohol, this sterol. Now, it's not exactly the same structure as progesterone down here at the bottom, but you're so close with all those rings in there and all those stereocenters. With a few transformations, you can convert that into progesterone, and then eventually make the money carbon-carbon bond by adding in sodium acetylide, just like you learned in class, to the carbonyl in order to make this tertiary alcohol, and then you work it up with excess water to protonate that. And that was the first orally available, or a component of the first orally available birth control pill. Now, the problem with Barbasco yams is it comes from another country, and there's all kinds of ethical issues about using their farmers and paying them a pittance in order to make a high-value product that's sold for a lot of money in the United States. And eventually just political issues and trade issues got in the way, and it became unviable commercially to make steroids like the ethinyl estradiols and those types of compounds from these yam sterols. And mainly that's because of this competing industrial process that was developed by Percy Julian. Percy Julian realized you could get sterols in small amounts out of soybean oil or out of soybeans. And the process of extracting out oils from soybeans, you also can extract small amounts of steroids, much smaller than the amount you get from a Barbasco yam, but we grow a lot of soybeans in the United States. Right? Even back in the 1930s, we were growing a lot of soybeans in the United States. In 2018, the U.S. soybean production was 4.4 billion bushels. I don't know how many pounds is in a bushel, but right, a bushel is more than a pound. So, the scale in which we produce soybeans in this country, even if you're getting a small amount of sterol out of the soybeans, right, you can make a lot of sterol. And that converting the soybean sterol into these steroid molecules that are important for as drugs turned out to be the viable process. It ended up supplanting the Barbasco yam process. And this is now widely known as the Glidden process, as opposed to the process that was developed by Syntex and their co-workers using the Barbasco yams. So hats off to Dr. Percy Julian and the Glidden process for manufacturing all kinds of steroid drugs, starting with soybeans. On Wednesday, we were talking about acetals and how to make them using carbonyl compounds. So you take an aldehyde or a ketone and toluene sulfonic acid and then some sort of an alcohol, and you can make acyclic acetals and cyclic acetals. And I wanted to break down that process mechanistically and think about what's going on in those reactions. Let me go ahead and start off by drawing out the starting materials for acetal formation. That would be either a ketone or an aldehyde. And you need two equivalents of an alcohol or alcohol hydroxy groups. So I'll go ahead and symbolize that by drawing 2ROH as our generic alcohol. And there is a key intermediate, a key mechanistic intermediate that you go through mechanistically en route to synthesizing an acetal. So if you add just after the addition of the first equivalent of the alcohol, you get an intermediate that's known as a hemiacetal. Hemiacetal. That means half acetal, but I don't think people like to use the word half acetal because it sounds kind of obnoxious. So they call it a hemiacetal. And then this undergoes an SN1 type process where you substitute the OH for an alcohol. And it's SN1 because there's no nucleophile in that process, in the initial addition step. That would be an SN2 reaction. So it's not, mechanistically, it's not a direct displacement. You go through something like a carbocation. Now, these are not one-step mechanistic transformations that I'm drawing out over here. And then the byproduct of this would be water. I'll draw it out with all those bonds. You can see where the bonds come from. The oxygen and the carbonyl ends up in the water molecule. And this final product here is referred to as the acetal. When I hear this name hemiacetal, it reminds me of this class of muscle car engines called Hemis because of their hemispherical shape. Super high power, powerful engines from the 1960s and 70s, Hemi engines. Okay, so you go through a hemiacetal intermediate, and hemiacetals are important not just as synthetic intermediates, but it turns out there's cyclic versions of hemiacetals that are particularly important for biology and biochemistry. Let's go ahead and take a look mechanistically at what's going on with this acetal formation mechanism. Now I'm going to go ahead and start off over here by drawing out my carbonyl compound, my ketone, maybe on its side. It just feels like it's going to lead to an easier way to depict this. So that could be an aldehyde or a ketone. And you have to have a powerful acid in here. I told you the recipe that we most typically use is toluene sulfonic acid. But you could also use hydrochloric acid or sulfuric acid. They're just not as convenient to measure out. Let me depict our since this is an arrow pushing mechanism, I'm going to depict our acid with the symbol HA. That's just more convenient. We don't have to worry about what acidic species is protonating it. Whoops, my arrow is starting from the wrong place there. Let me draw the lone pair. So you protonate the lone pair on oxygen. Here we go. We're going to pick up a proton, and we're going to generate a protonated carbonyl, which is a super important synthetic mechanistic intermediate. Let me go ahead and draw out that protonated carbonyl. As soon as I see that oxonium ion with the positive charge on oxygen, 3 bonds to oxygen, that's got to have a positive charge. It's called an oxonium ion. So whenever I see that oxonium ion, I feel like I want to attack that with something. So even water and alcohols can attack that now that it's got a proton on there. So let me go ahead and draw an alcohol molecule that's poised right nearby. And there's the lone pair on there. And so now we'll draw that alcohol attacking. So easy to attack that. And it just feels so good to give the electrons in that pi bond to the O+. Oxygen does not want to be positively charged. You know, I think at some point early in organic chemistry, you probably learned that you should attack carbocations that are C+. But that's because the carbocation only has 6 electrons. That oxygen's got 8 electrons. Don't attack that oxygen. There's no rule that says you always attack things with positive charges. You attack carbon atoms that only have 6 electrons. That's the rule. And by attacking this carbonyl, we can get rid of the positive formal charge on the on that oxonium oxygen atom. Let me go ahead and draw out this next intermediate here. I'm going to have this alcohol group here, and I'm going to draw the OH bond because I know in the next step I need to remove that. And so now we have this tetrahedral intermediate. The alcohol that just attacked is going to be an oxonium ion because it has 3 bonds to that oxygen. And now I want to get rid of that proton. So there is an A- floating around. It was still here in this previous step. Let me go ahead and draw it down here right next to that proton so we can see that it's about to pull the proton off. Let's pull the proton off of that oxonium. There it is. And so now we've got our hemiacetal intermediate. There it is. That's our hemiacetal. So it's kind of a lot of steps. 3 steps in order to generate this hemiacetal intermediate. And now we still have that HA floating around. Our catalytic acid just got regenerated in that last step. So let me go ahead and draw that species there. And the next stage of this process, so this is our hemiacetal intermediate. Let me go ahead and label it as that. Hemiacetal. Hemiacetal. Now we're going to do an SN1 reaction. In an SN1 reaction, you pop off a leaving group, and then in a second step, the nucleophile attacks. That's how you define an SN1 reaction. So let me go ahead and draw out those the arrows for that. I'm going to protonate this alcohol and turn it into a leaving group, and then it's going to leave, kind of. And so the next intermediate now has that water protonated and just ready to act as a leaving group. Here it is, OH2 plus on the oxygen. And now it's not just that the water is going to leave. Let's be a little bit more specific than that, because this is just an amazing, amazing ionization. Why didn't they start off Chem 51 with this reaction? Because this is the kind of ionization process where a leaving group leaves easily, but it's not just that it's leaving easily, it's getting pushed out. That's why that's such a facile ionization. That's better than any carbocation forming reaction you ever learned about back in the first quarter of organic chemistry, right? This is what it looks like to do a good SN1 reaction. So let's go ahead and follow that through. We're going to end up with this intermediate now, where again, we have 3 bonds to oxygen. Don't attack the oxygen just because it has the positive charge. You want to attack the carbonyl carbon. This should look kind of like a protonated carbonyl group. So now we come along with our another molecule, another equivalent of our alcohol. I'll draw it down here and draw a lone pair on there. And that's going to attack that carbonyl carbon, what used to be the carbonyl carbon. It looks sort of like a protonated carbonyl. We'll attack that. Don't attack the O+. And then we'll give the electrons in the pi bond to the oxygen plus. And so that's going to give us another one of these intermediates where we have this alkoxy group over here that just attacked the alcohol molecule just attacked. And now all we have to do is deprotonate. And if you remember back over here, we generated A- as our counter ion in this reaction. So let me just go ahead and draw the fact that there's an A- just waiting patiently around there. And over here, there's an A- to offset the oxonium plus. And that A minus is still here. And so let's go ahead and take advantage of that A minus to deprotonate this intermediate. And that's what gives us our final, the final product in this mechanism, which is an acetal. Let me see if I can squeeze this acetal in here. There it is. And that's our acetal. And that's the mechanism. It's a long mechanism. Acetal. That's the mechanism for acetal formation. Now, if you take an acetal, you can treat it with any bases you want. It's not going to touch this. It's not going to deprotonate it. It's not going to substitute it under basic conditions. It's only under acidic conditions. You know, under acidic conditions, you can protonate things and turn them into leaving groups. Under acidic conditions, you can hydrolyze acetals simply by using water as the solvent instead of alcohol. It drives the equilibrium back in the other direction. And the mechanism involves the same intermediates. There's 1, 2, 3, 4, 5, 6, 7, 8 intermediates or structures. And if you did acetal hydrolysis, the intermediates would be the same, but the arrow pushing would be different. So you can go ahead and review the mechanism for acetal hydrolysis. You'll see the same types of intermediates in the book in that next section, 21.14b for the Gorzhinsky-Smith 5th edition of the textbook. Let's go ahead and take a look now at how do you use acetals. They're useful synthetically. And the particular problem that they solve is this problem of, what if I want to do chemistry under nucleophilic or basic conditions, and I've got some ketone or aldehyde and I don't want to mess with it? So how do you deal with that in synthesis? Well, one thing you can do with a ketone or an aldehyde is you can mask it as an acetal, which doesn't react with nucleophiles or bases. So if we wanted to make a Grignard reagent out of this, if you don't do anything, then the Grignard will start to attack the carbonyl, and you wouldn't be able to do any of the chemistry you want. So we want to hide that carbonyl so it doesn't get messed up by creating a Grignard reagent under the conditions of the reaction. So how do we make an acetal? I already showed you conditions for doing that. There's one alcohol that's common, and that's ethylene glycol. So it's way more common than just making an acetal with methanol. You get higher yields with the cyclic acetals. And we need a catalytic acid for this. Remember the catalytic acid I told you about? Toluene sulfonic acid. It's a solid. So convenient to just measure out a little bit of this powder on a balance. You can weigh 2 milligrams, 5 milligrams. A lot easier than measuring out microliters of sulfuric acid, which is corrosive to whatever you use to measure things with. Well, that's going to generate this 5-membered ring cyclic acetal. And let me go ahead and draw that out. And so now that acetal is masked. And you can make Grignard reagents. You can put alkylithiums in here. They won't touch that thing because the conditions, all of our other conditions now aren't going to be acidic. When we make a Grignard reagent, those conditions are going to be basic. So I'll show Grignard reagent formation. You just add magnesium to that. So we draw that bond. Now it's a magnesium bond. And the bromide is attached to the magnesium. Or a super nucleophilic bromide magnesium, bromomagnesium carbon bond. There we go. And now we can make carbon-carbon bonds. As soon as I see a Grignard reagent, I want to add it to a carbonyl. So let's throw some carbonyl in there, and we'll try to make a new bond. And for my carbonyl, let's go ahead and throw in acetaldehyde. That's a simple, easy carbonyl that we can add. Step 1. And remember, we have to work those reactions up with water as a workup. So aqueous workup, step 2. And so the product we would get, let me try to draw all these things as similarly as I can. That acetal won't be touched because the conditions for that for making this Grignard reagent and adding to carbonyls, those are basic conditions. And so let me go ahead and draw the new bond we form. So there's the new acetaldehyde attached to there. So there's a new bond that we just created. And that acetal will just keep sitting there. And so now we've got to get rid of that acetal. And so how do we do it? We throw in an acid, and instead of using ethylene glycol, we use water as our solvent. So we throw in a catalytic acid. It could be toluene sulfonic acid. I'll write toluene sulfonic acid. But when you're hydrolysing acetals, you just want to dump a bunch of acid in there. We usually keep bottles of hydrochloric acid on our shelves rather than you have to go get the bottle of toluene sulfonic acid and weigh it out of the balance. So usually people just pour in some hydrochloric acid. This isn't like imine or enamine formation where we're using acetic acid, which is a weak acid, right? This kind of chemistry for getting oxygen atoms to attack carbonyls, we need strong acids. And so this would finally generate our product. Right, the conditions, you don't mess with just simple alcohols. Acetals are much more reactive than than regular OHs, or so you don't have to worry about any E1 chemistry going on with that hydroxy group. Okay, so you can take aldehydes, you can mask them as acetals, do stuff, and then unmask them. That's protecting group strategy. We've shown you another protecting group you can use for hydroxy groups. Remember, that was the tert-butyl dimethylsilyl group that we could put on quantitatively and take off quantitatively. So you know how to protect alcohols so that you can work with bases and nucleophiles. And now you know how to protect aldehydes and ketones so that you can work with bases and nucleophiles without messing them up. Okay, generally, hemiacetals are not stable. So, right, if I take just a simple hemiacetal that looks like this, you can't isolate that. It'll automatically revert back to just an aldehyde and an alcohol. That's where the equilibrium lies, is the carbonyl side. But there is one class of hemiacetals that is stable, and that is cyclic hemiacetals. So if I were to synthesize this hydroxyaldehyde, it would cyclize automatically. You can't control this. It would cyclize automatically to give you a cyclic hemiacetal. So that's a stable hemiacetal. But it depends on the ring size whether those cyclic hemiacetals are going to be stable. So let me go ahead and give a name here to each one of these forms. I'll call this the closed form, so we have something to talk about. And I'll call this the open form. But really, instead of the closed form, I ought to call this the hemiacetal form. Hemiacetal. I could call this other side the aldehyde form, but I feel like open and closed will make a little bit more sense. Aldehyde. Boy, I'm not very good at writing on this. Whoops. Wow. Aldehyde. There we go. So the closed form and the open form are in equilibrium. If you make the hemiacetal, it'll equilibrate to give you some of the aldehyde form, the open form. And if I synthesize this hydroxyaldehyde, it'll equilibrate to give some of the closed form. But it depends on the ring size. 6-membered rings are extremely favorable in this case. So this ring over here, the 6-membered ring, exists in a 94:6 ratio. And there's nothing you can do to change that ratio. That's governed by free energy and an equilibrium constant. So as long as you put it into solution, it will automatically equilibrate. 5-membered rings are also very favorable. But when you try to make strained rings, like 4 3-membered rings, you're not going to be able to get any of this cyclic hemiacetal form if it's a 4-membered ring. And larger rings, 7, 8, 9, you can't do it either. It's only 5 and 6-membered rings that have this property where this hemiacetal, the cyclic hemiacetal form, is stable. Let's go ahead and take a look at the mechanism that's going on here, because the mechanism is acid catalyzed. Even if you don't specifically add acid to your beaker, if you've got hydroxyaldehyde, it will undergo an acid catalyzed mechanism for ring closing and ring opening. So let's go ahead and draw out that mechanism for the reaction. And I'll start off over here with, there's the hydroxyaldehyde form, and I'll symbolize the acid under these conditions with the symbol HA for arrow pushing. Let's go ahead and draw out the electrons and the carbonyl, because we really want to protonate that carbonyl in order to get the hydroxy group to attack at fast rates. Oops. So now we've got this protonated carbonyl that's so easy to attack. Boy, I just really want to attack that protonated carbonyl. I'll put the positive charge on there. Don't attack the oxygen, attack the carbonyl. So let's do that. Let's go ahead and give the electrons in that hydroxy group. We'll make them attack that protonated carbonyl. It's so easy to attack. and we'll give the electrons to the oxygen. Wow, that just feels great to attack carbonyls that have oxonium oxygens, positively charged oxygens on them. So now we've got this cyclic intermediate over here. And we still have this annoying proton over here on the OH that acted as the nucleophile. I'll draw the positive charge over there. Now, how are we going to get rid of that? We've got an A- floating around, so let's draw that in. When we deprotonated in step 1, we generated this counterion A-, and now we're ready to use that. I'll use that as a conjugate base now to deprotonate, and that leads to this cyclic hemiacetal intermediate. It should look like the mechanism that I just showed you for the acyclic acetal, except it's cyclic. And so that's the mechanism. Same as hemiacetal formation. It's good practice to write that out and get used to these protonating carbonyl groups so that we can get oxygen nucleophiles to attack the carbonyl group. Now, those intermediates are going to be particularly important. It turns out that these 6-membered ring and 5-membered ring acetals are important in biology. So let's go ahead and talk about some of the transformations. They're just really great for SN1 substitution reactions. So, right, substitution, if I have an OH on a hemiacetal, I can substitute that with an alkoxy group. And substitution is way easier than SN1 type reactions. This is still an SN1 process, but it's way easier and more facile than SN1 type substitution processes that you might have learned about earlier in the organic chemistry series here. So what do I want to substitute that with? Well, maybe a methoxy group or an ethoxy group. It's pretty easy to do. You want to use an excess of these. So I'll draw the methanol below the arrow. That indicates that it's solvent in an excess. That'll drive the equilibrium towards this side by Le Chatelier's principle. There we go. And so this is going through an SN1 process. And you get super high yields for these types of substitution processes. The 5-membered ring system would also work well. So let me go ahead and draw out a 5-membered ring. In this case, I'll start with the hemiacetal, the mixed acetal, and we'll hydrolyze it. You just, instead of using alcohol as your solvent, you use water. And that'll replace the ethoxy group with a hydroxy group. And you could use catalytic HCl. I'm going to write catalytic toluene sulfonic acid just because it'll look like the same acid that you use to make the acetals. And so in this case, we're going to substitute ethoxy with hydroxy. Now, in these cases, it's SN1. You go through an intermediate that's kind of like a carbocation. It is a carbocation. But that means you can't control whether the hydroxy group attacks from the top or the bottom face. It doesn't matter what stereochemistry you started with. Even if I started with 1 enantiomer of this acetal, you can't control whether the OH adds from the top or bottom. So you're going to get a mixture. Half of your material will have the hydroxy up, but the other half of the material is going to have the hydroxy group pointed down. And it's the same for this top case where we make the 6-membered ring. You would get a mixture of 50% of your molecules would have the methoxy up, and then the other 50% of your product would have the methoxy group down. These types of 6-membered ring acetals are super important in biology and biochemistry. The 6-membered ring acetals are important in sugars like glucose, galactose, mannose. The oligosaccharides composed of these sugars are found on the proteins that coat the surface of cells, not inside of cells, but extracellular decorations that are important for cell-cell recognition and immune response. 5-membered ring hemiacetal type intermediates, well, that's ribonucleic acid. This is a ribosyl type system. This furanose ring is like a ribosyl system like you find in DNA and RNA. So I'll just write here like DNA and RNA. This is where you'd find these kinds of 5-membered ring intermediates. And usually you have a nitrogen atom attached instead of an ethoxy group there. But it's the same idea. Chemically, it's the same idea. Okay, let's try to think about what's happening mechanistically here with these mixed acetals. I mean, let me just start off by taking advantage of the acid that's present in our reaction mixture. So if I take this kind of a cyclic hemiacetal, and I want to draw a mechanism for substituting that hydroxy group. Let me go ahead and take advantage of the acid first. The reaction occurs under acidic conditions, so I'll symbolize the arrow pushing acid as HA, because we don't really care what the species is that's transferring protons. We just want to symbolize it. And now both of these oxygens have lone pairs on them. So you'll protonate this oxygen and then pull the proton off. Then you'll protonate this oxygen and pull the proton off. Protonate this oxygen, pull the proton. All that's happening in solution. So neither one of these oxygens is more basic than the other. But if we want to explain how you substitute the hydroxy group, then we better draw that as part of our mechanism. Start here. We're not saying that you don't protonate the other oxygen, but we only want to show the steps that are leading towards the product, which is going to be substitution of the hydroxy group. So it may be frustrating for you that we don't show everything that's happening. We're just showing the things that lead to the products, the steps that lead towards products. So this converts that into a great leaving group. So get ready. We're going to use that as a leaving group in just a second. And it's not just that it acts as a leaving group. Right? That would not be completely accurate. This lone pair over here on the ring oxygen, this 6-member ring is called a pyranose ring. That's important for the reaction. Earlier in the organic chemistry series, you learned that protonated alcohols could act as leaving groups to leave with water. Those aren't very good. It's not very good to give a secondary carbocation. But the reason why that water leaves so easily is because it's getting pushed out. It's not just leaving, something is pushing it out of there, right out of there. Man, that looks great to use neighboring lone pairs to push out leaving groups. And so that's better than any SN1 type ionization that you ever saw earlier in the organic chemistry series. And so we'll get this species here that that looks a little bit like a protonated carbonyl. Right? There's the species, and that can now be attacked. Now, if it is like an SN1 reaction. We don't usually depict this other resonance structure. There's another resonance form that we could draw here that looks like this. So here's the other resonance structure we could draw. But get over it. You don't need to keep seeing carbocations. What I'd rather you do is got used to doubly bonded oxygen. So if we've got alcohols that are present here in this reaction mixture, those alcohols are going to attack. So let me go ahead and draw that. And so let's use this top resonance structure. Oh, that just feels so good. Man, don't attack the O+. You attack carbocations because the carbon only has 6 electrons. Well, don't attack the O+. It's got 8 electrons. You're not going to get rid of the positive charge by attacking it. You're just going to end up with too many bonds. That would be really freaky. I didn't do a good job drawing that lone pair, so let me just draw it there. So don't attack O+. It's already got 8 electrons. Attack the carbonyl carbon and give the electrons to the oxygen. So it gets them all to itself. Okay, so let's go ahead and draw this mechanism. I'm just going to avoid that the old-fashioned resonance structure from earlier in our Chemistry 51C series. So we're almost there at our mixed acetal, our mixed cyclic acetal. We just have to get rid of this proton. And if you'll remember, right, in our initial step, we generated this A- counterion that's just been patiently waiting around there. There it is. Let's go ahead and use that now. I'll draw it over here on this side. And we'll deprotonate that oxonium ion intermediate. Oxonium means oxygen with 3 bonds. We give the electrons back to the oxygen. And so now we end up with our mixed acetal, and it's cyclic, so those turn out to have special stability. And this is starting to look a lot to me like glucose derivatives or glycosides that you find in biology classes. Now there's a whole section, a whole chapter in this book on carbohydrates, on glycochemistry, glycobiology, and glycans. And understanding the chemistry of these cyclic acetals is setting you up to understand the chemistry of carbohydrate derivatives. So Chapter 21 gives you a little bit of a lead into that, even though we're not covering Chapter 27 in our course. I think it's worth reading and learning about that, so go ahead and read it. But I'm not going to ask you to memorize the structure of glucose or fructose or any of those other sugars. It's not really the kinds of questions that I ask in my class, those kinds of memorization questions, but it's still important if you're going to take classes in biochemistry here at UC Irvine or elsewhere, or take standardized exams like the MCAT or the DAT. All right, that's it for our lecture today. So, just keep working problems. Next week during discussion section, we're going to be practicing these reactions of aldehydes and ketones with ylids, doing Wittig reactions, maybe the chemistry of imines or enamines, and then acetal and hemiacetal chemistry. So keep working problems, and I will see you on Monday. Have a great weekend.